Heat Operation Classroom. Today we are discussing parallel reaction selectivity in different plug flow reactor configurations. My name is Shekhar Bhattacharjee. Consider the following homogeneous isothermal constant temperature liquid phase no change in volume. Parallel reactions carried out in three reactor configurations. We will see what are those reactor configurations. All three reactor configurations have identical volume, and same operating temperature. Okay, what are those configurations? In the first PFR, we see there are two reactants, A and B. Reactant A is fed through several side streams, whereas the entire fluid B is entering the plug flow reactor. Uh, Here, FA0 is 10 moles per minute, so this is 10 moles per minute, and Ca0 here, Ca0 is 1 mole per liter. So therefore, the flow rate of A is 10 liters per minute. So here A is entering at 10 liters per minute and at a concentration of 1 mole per liter. And if I assume, of course, there are not 10 points here, but let's assume if there are 10 points, so at each point, we'd assume 1 liter per minute or 1 mole per liter of A would be introduced. Whereas entire B, just 10 mole per liter, again 10 liter per minute, same concentration. So 10 liter per minute here, 10 liter per minute, entire 10 liter per minute of B of concentration 1 mole per liter is entering here. So that is the first reactor configuration. And there are two products. The one product is desired product and the other is the undesired product. We will see that. What is the second configuration? The second configuration, both the entire 10 liter per minute of A and the 10 liter per minute of B enter right at the entrance of the plug flow reactor. And what is configuration 3? See, in the configuration 3, here, the entire 10 liter per minute of A is entering here, and this concentration 1 mole per liter. But here, B is entering as a side stream at several different points. Let's say if there are 10 points, so there'll be 1 liter per minute of B entering at each of these points. So here, A is entering as a side stream, and here B is entering at a side stream. Okay. So these are the three reactor configurations. What are the reactions taking place inside the reactor? The first one is A plus B, giving the B as a desired product, and the rate of reaction is first order with respect to A and first order with respect to B. And the second reaction is parallel reaction is A plus B giving you an undesired product U. And here the rate of reaction is proportional the second order with respect to A and the first order with respect to B. So that's what it says. And Ca0 and 1 mole per liter, etc. we have discussed, and Fa0 is equal to Fe0 10 mole per minute. So in configuration 1, FS0 is equally distributed among all inlets. Similarly, in configuration 3, FP0 is equally distributed among all inlets. Assuming flush flow behavior at steady state, which one of the following statements is correct? Okay. So what are the statements? Configuration 1 and configuration 3 give the same selectivity. We'll see how we define selectivity of the desired product. Configuration 1 gives the highest selectivity of the desired product. Configuration 2 gives the highest selectivity of the desired product. Configuration 3 gives the highest selectivity of the desired product. We have to find out which option is correct. And also, instantly, the volume of the plug flow reactor in all these three cases is the same, and the operating temperatures of all these three reactors are, of course, the same. So first, let's see how we define the instantaneous selectivity. What is instantaneous selectivity? Of course, we know the concentration of A and the concentration of B keeps on changing and keeps on decreasing as it goes along this direction. Yeah, but at any point, the rate of reaction of the rate of formation of D with respect to rate of formation of U is defined as the instantaneous selectivity. So this is S to D over U. So this is given, D is the desired product and U is the undesired product. So you can see this instantaneous selectivity anywhere inside this reactor. At any point, the selectivity is inversely proportional to the concentration of A. So if we can keep the concentration of the A as low as possible, then we can achieve the highest selectivity. That's the idea. So we have this reduces to the point in those three configurations where we can maintain the effective concentration of A low as much as possible, which gives the lowest one. So to increase the instantaneous selectivity toward T, CA at the position of PFR should be low, and S is independent of CV because both of them are with first order with respect to CV, so these two cancel out. So the concentration of B inside the reactor does not affect the selectivity, although it affects the rate of reaction. So let's look at configuration 1. Here, as I say, that 10 liters per minute of A at concentration of 1 mole per liter. If we assume there are 10 points, so each point will have 1 liter per minute of A entering. So these are effectively very small concentration, whereas the entire B of 10 liter per minute is entering here. Okay. So if I assume 10 points, say each point will receive 1 liter per minute approximately. So CA concentration is effectively small all along the length of the reactor, So staged addition of A keeps CA relatively low, giving undesired U formation relatively suppressed more than the desired D production. Okay, so configuration 1 gives the highest selectivity because we have seen if we can keep the concentration of A as low as possible, then the instantaneous selectivity will be very high. So here, just by distributing the flow of A at 10 different points or 11 or whatever n number of points, we are effectively keeping this concentration of A low, and therefore this will give the highest selectivity. Let's look at configuration 2. Here both A and B entered at high concentration. So CA0 is 10 liter per minute or 1 mole per liter. CB0 is 10 liter per minute or 1 mole per liter. So effectively CA in and CB in is 0.5 mole per liter. And of course, as it goes, the reaction takes place, and of course, this concentration of A and B are decreasing towards the exit of the PFR. So highest concentration of A, 0.5 mole per liter at PFR entrance, right here, where rate of both desired and undesired reactions are highest. Okay, because the rate is proportional to concentration of A and concentration of B. These are the highest at the entrance. So rate of undesired production is second order, desired production is first order. So S is lowest at the PFR entrance. So here the concentration is very high. So we have the lowest selectivity D over U to B over U at this entrance, but then it's improved as it goes on and because the concentration of A is decreasing. Nevertheless, so along the PFR length, CA also CB decreases and S increases. Nevertheless, overall selectivity, instantaneous selectivity in configuration 2, that means here, is less than the overall selectivity in configuration 1 here. Okay, so between configuration 1 and 2, this has higher selectivity. Next, look at configuration 3 here. So here what happens, the entire A is entering here, whereas B is distributed at n number of different points, let's say 10 different points. So B so in at PFR entrance, CA0 is highest, B concentration is low throughout the PFR level, as only a small amount of B Say 1 liter per minute, if we have 10 points, is injected at each point. Since CB is low along PFR length, CA remains relatively high along PFR length, favoring undesired information. So among the three configurations, configuration 3 has the lowest selectivity, that means this one, which is less than the configuration 2, which is less than the configuration 1. So here, if we can see here, this one has the lowest selectivity. This one has a slightly higher selectivity than this one, but lower than this one. And this one is the highest selectivity. So, assuming plot flow behavior at steady state, which one of the following statements is correct? So let's look into it. Configuration 1 and 2 give the same selectivity of the desired product. We have seen that's not true. Configuration 1 gives the highest selectivity of the product. That is true. So this is correct. Configuration 2 gives the highest selectivity of the desired product. That is not true. And configuration 3 gives the highest selectivity. That's not true. So this B is the correct option. Let's look at the practical application of this staged reactant addition to a PFR. This problem. What's the practical application? Let's say propylene oxidation to propylene oxide using hydrogen peroxide. This is the familiar reaction. Hydrogen peroxide is introduced in stages here, different stages, into a propylene-rich stream flowing through a tubular reactor sections. This limits local hydrogen peroxide concentration, suppresses decomposition of hydrogen peroxide, which easily decomposes, and side reactions, and giving all other oxidation products of this one. We don't want that. We want this particular one, that is propylene oxide. Improves propylene oxide selectivity and enhances process safety.